Okay, welcome back. Let's dissect Norton's theorem now. We have looked at all our resistance values. I hate to have to do that symbol. It's a little bit problematic. So the omega symbol. So now for our resistors is going to be in ohms. I'm just going to put numbers here. I'm just going to state. I stated already there that our resistors are in ohms. Now when we deal with Norton's with Thevenin's theorem, what we do, we reduced our network into what? Into a resistor and into a voltage at a certain point and the resistance looking into that point. So with Norton's theorem, what we do is we reduce our network, our entire system, into what? Into a current source and a resistance at that point. So now, whereas Thevenin dealt with a voltage source or an EMF with the Thevenin resistance, Norton deals with the what? With the current source and Norton's resistance. So what do we mean? We mean that with Thevenin, we said what voltage exists at the point of connection, and we call it V Thevenin. And you said what resistance looks into that point, and you call that R Thevenin. And you said they look at the point where our loads are going to be connected, right? Where our loads are going to change. So with Norton's, I'm saying we do not worry about this. We still worry about the resistance, but we deal with the current source rather than a voltage source. So this is going to be, with Norton, we're going to have a Norton's equivalent at the point of connection, Norton's equivalent current at the point of connection, and you're going to say what is the resistance that already taps into this source, so that when we connect ours, it's going to share with the existing resistance of the system. So this is what it will look like at the end. You're going to have a current source, Norton's current source, and you're going to have what? Norton's resistance, and we are going to connect our load at that point. We still have our point of connection where we are going to connect. We can still call it A and B. This is, whereas previously with Thevenin, a voltage source looked at this point or arrived at this point, a voltage arrived at this point, and the resistance looked into this point, into that space. And in this case here, it's going to be similar, but except it's going to be current and resistance. How do we calculate the what? Norton's resistance? It's the same as Thevenin. This is same as Thevenin. Rn, same method, as RTH. What do? We remove the load and we replace the source with the what? With the equivalent resistance, and we calculate. So this will still be the same as what we got last time. What did we do? We said remove that one, remove this one, okay, and then what do? You name those points A, B, and you say when you connect, what system resistance are we going to see? That does not change. This is our A, or rather, let me change it. I know where I'm going. Decorative table. I know where I'm going, so this is our A. This is our B. I'm putting it in here because I know where I'm going. Now, these, we have removed the load. RL is equal to 1 has been removed. So, let people have defective vision sometimes, so let's make it clear that it's been removed. What we then do is, calculating this is still the same. We replace that with the what? We replace that with the what? With the resistance. So our R here is not mentioned, so there our R is equal to 0. So our R here, unless it's mentioned, our R here is equal to 0. So meaning that this line here has a resistance of 5. So we are going to start with R parallel 1. R parallel 1, not R1, R Norton, same as R Thevenin, which means, no, R Norton, same as R Thevenin, which means we're going to have R parallel 1 being the 5 and 0 parallel to 4, 5 and 0 parallel to 4. So that will give us, remember our values are already in ohms, that will give us 20 over 9, which you should not forget, that's 2 and 2 over 9. Right, I have my calculator now, so if we wanted to do this, we could say 2, okay, no, 20 divided by 9, and you would have a value of, I should have seen this, I should have known this, 2 comma 2 recurring. Okay, this is our ohms. All right, now we should know the habit that when you do a calculation, because we may use, and I know definitely we're going to use this one, we may use it in subsequent calculations. What we do, let's use our store function. If you look at our scientific calculators, you will see a store function STO. I'm using a Sharp advanced DAO EL531WH, and there the store function, you'll see it's STO. It's written there in green next to the recall function RCL, between the recall function and the M plus, the memory plus. So I will say I want to store this answer, so I just hit STO. You see an alpha on the screen there, and you just say it's a blue function, so you can see the A, B, C, D, E up to F, they are in blue. So you then say choose the A because it's a first calculation, so it tells you the A is stored. I don't know if you can see that. It will say A is stored in A. I'm going the wrong direction. Answer stored in A. As you can see, answer stored in A. I'm trying to run away from the reflection. So it tells you my answer now is stored in A. Let's go on and say okay, because if I want to, why do I do this? I don't want, because for me to write, it will be easy for me to write 2.222 and say 3 decimal places. Now when I calculate, I'll be tempted to use 2.222 as in my calculation, which is very wrong because I'm ignoring the rest of the answer. Okay, so always when I'm going to use when I'm going to use this answer in subsequent in following calculations, I need the whole answer as it is, the original answer as it is, not the rounded figures that you tend to write for convenience. So I've stored my answer in A. So next time I want to use this, I'm simply going to recall my answer from A and use it. Now we go on and say that's our R what? That's our R parallel 1. But that R parallel 1 is connected in series to the what? I'm going backwards, you see? This is closed, so I'm going backwards towards the open. So now this is going to be in series with the what? With the 3 ohm. So I'm going to then go on and say my next calculation is R series 1 is the first series value I'm calculating. R series 1 is going to be the 3 ohm in series with R parallel 1, which will give me 3 plus what the 3 plus 2 comma 2 recurring. I missed this last time, that was just a recurring number, which will therefore give us what? Which will then give us a 5.2 recurring. I've already said all my answers are in ohms, so I'll be forgiven for not including the ohm symbol there. Now, this is our what? Our R series 1. Now our R series 1, once we've got a series value, there's like one value, as you can see, it will be in parallel with the 2 ohm. So we'll say R parallel T, second parallel calculation we're doing, is going to be equal to what? The 2 ohm parallel to R series 1, which is equal to 2 times 5.2 recurring over over 2 plus 5.2 recurring. I should in fact have I should in fact have said plus 3 previously for my second answer. Plus 3. Don't know whether this is going to be clear. I can't make it look 3 plus 3. And I should have stored my answer. Store this answer in B. Again, I say STO and I say B. And you can see there, our answer is stored in B. As you can see, I'm trying to run away from the reflection, but as you can see, answer with the arrows there stored in B, and it's 5,222. So I know when I need to use that answer, it's in what? It's in B. I normally put in pencil a little B here to remind me, I know an A there to remind me. When I'm now quick, I may forget where I stored what, and I have to keep running through the stores. To avoid that, I normally put in pencil a little B here to indicate that I've stored my answer in B. Now, then I go on and say, this now is going to be, now I need this answer. I'm simply going to say this times 2 equals 2. Then I'm going to divide that answer by the sum of 2 plus recall B. RCL, the one next to the function, I say recall B, and I say, as you can see, my answer now says 1,446. What is this now? This tends to happen a lot. 446, and it's in ohms. I know this is 3 decimal places, not my actual answer is 3 decimal places, so I indicate that I've rounded off to 3 decimal places. Okay, so this is our answer for the what? For this parallel network here, where that network, the RCS1, was parallel to the 2 ohm. We still need to add that to give us our R Norton. R Norton therefore is equal to the 3 ohm, the final one there, plus that whole parallel network there, which was what? Which was R parallel 2, which is equal to 3. I stored my answer. I didn't store this answer here. Store this answer in C when I need it. I know how to get it. So this is 3 plus, it will be wrong for me to simply add 1,446. I have to add the original answer with the 1,4615 whatever, and terminates again when the calculator is what? When the number of digits the calculator can display has been exhausted. So it's still going on. I'm sure that number is still going on. So this here is still just 3 decimal places, and our answer is going to be, I say store this answer plus 3, and I say store this answer here in what? Store this answer in T. So for calculation, so this is going to be 4,446, and this is what? Still 3 decimal places. This is not my answer. My answer is much longer than that. I'm just, so however, my actual answer is here. When I need to use it, I go back to the stores and I just recall my T and I use my answer. Okay, it will be wrong again. Each time I calculate and round off and calculate and use that rounded off figure in a subsequent calculation, I'm losing value from my what? From my actual answers. So therefore, I'll be going off. And it may be dangerous in the case of calculating certain, let's say, angles of beams, for instance. You end up being off, and then that could be a dangerous structure. So we need to be careful about that. Now, this is our R Norton. It's been done the same way that we did the Thevenin before. So there's nothing new here. All right. We go on then to say how then do we do I Norton? To do I Norton, that whole structure here has to what? It has to be, we have to calculate the current between points A and B. The only way we get a current between A and B is if A and B are closed. Because if it's open circuit, there can be no current there. So what we do, we short circuit the 2 points. When you short circuit the 2 points, now we've got a current from A to B. This is, I'm just saying, I don't want to interfere with the previous circuit, so all I'm doing is what we know how they did are being added, or they've just drawn a line here. Okay, I want us to remember how we did R Norton. So now we're doing I Norton. I Norton is the one that flows if there's a short between A and B. It's the current that flows between A and B when the circuit is closed. How do you close it? Not with the load. The loads can change. You close with the what? With a short. So to calculate I Norton, we have to do lots of calculations because now we have to start. Remember now that the source has to be there for us to have current. So these two now, because this circuit is closed now, the 3 and the 2 are now in what? Are now in parallel. We will call it R parallel. Okay, let me show that I'm now doing I Norton. For I Norton, I will say short circuit what is going on. It is busy writing things all over the place and not where I want. Oh, okay, I need a pen now. Short circuit A and B and calculate I Norton, which is equal to I A B. Okay, right now. So when you short circuit there, 3 and 2 become parallel. So we call that R parallel. But you already went up to R parallel 3, R parallel 2, so we call this R parallel 3. That will be equal to 2 parallel to 3. You shorted here, so this and that are now parallel. So this will be equal to 6, 2 and 3, 6 divided by 5, 2 plus 3, which is equal to 6 over 5. That will be 1, 2. Remember, we already stated that our resistor values are in what? Are in ohms. Now, when you've done that, you've got this value here in series with that parallel network. So therefore, we are going to talk of R series 2. And that will be the 3 ohm in series with R parallel 3, which is equal to, this is 3 plus 1, 2, which is equal to 4, 2. This is not the same as this. This was repeating. This is not repeating. The direct answer. Okay. So this here is going to be ohms. We already stated that. Then now we've got 3 and 3 and 1, 2. So we've got our 4.2. Now that value is going to be in parallel with the 4 ohm, as you can see. From there, 3 in series with that is in parallel with that 4. I don't understand why it keeps throwing in ink here. Something is wrong here. Now let's go and say we want R parallel 4, and it's not writing anymore. Oh, I've got rubber. Okay. R parallel 4 is simply the 4 ohm in parallel with the what? R series 2. That will be equal to 4 times R series 2, which is 4.2, over 4 plus 4.2. This is equal to, now if we look back, our R neutron, what will Norton is what we need. So I will take that my final answer there. Instead of taking it to T, I will store that answer in A, so that I can use B to do the new calculations now. These ones were all leading up to R Newton. I've got it. So now I need to do fresh calculations. So I'm replacing the old storages. I won't need them anymore. I will only need the final answer. So I've put it in A. I've moved it to A. So this is going to be 4. I'm doing a new calculation. 4 times 4.2 divided by 4 plus 4.2. So that gives me 2,049. This is 2,049. and this is already in ohms. We already studied that, so we store our answer in B because A is now taken by R Newton. So we store our answer in B. Our answer is in B. If you can see it, then good for you. If you can't, well, just practice. Practice makes perfect. I'm trying to show you that my answer there is stored in B now, except for the reflection. Now, we go on to say, once we've got 4 and that, this give us one value. That value is in series with the what? With the 5 ohm. So there is the 5 ohm. This is now R parallel 4. So our R total in this case is going to be equal to the 5 in series with R parallel 4. Why is that happening? Keeps happening a lot now. R parallel 4. So this works out to 5 plus 2 point something, 5 plus 2 comma, remember this was 3 decimal places, eh? This is not our answer. Our answer is longer than that. Okay, so this is 2 comma 0 4 9, and it's still 3 decimal places. I'm just doing this for writing. This is going to be equal to 7 comma 0 4 9, and this is what? This is still just 3 decimal places. This is not our answer. This is 3 decimal places, and we need to store our answer. Our 049 is in B. When we add 5, and our answer is 7, I store that in C. STOC, and our answer there, I've stored it in C. So now we then have the total resistance of the circuit. What you can get from that now is, do I really need to calculate the current, total current? I could, then I could keep doing the current divider. Is still fine. Okay, I've been doing voltage divider. Let me, for a change, do current divider to remind people. So we have now here that current here without the what? With a short. That current there is what? Is going to be our I total. All right. So that I total, I'm going to say I total. It's only applicable when we have a short here. Okay. So this is I total. Okay, so our I total now, when it comes here, it's going to be shared by this what? This parallel network. So it's going to be shared by 4 and R parallel 4. So it's going to be, I total is going to be, when you use this resistance here, R parallel 4, which is R parallel 4. Remember, in a parallel network, we use the other resistance for that current. So I want the current that goes through. No, in fact, I don't want the current. I'm calculating the wrong current. I don't want the current. I want the current through the 4 ohm. So I want the current through the parallel network, because the one that I'll keep dividing until I get here. So I want the current through the parallel network. So I want the 4. Just a reminder, when I've got a current coming through, just a reminder, a quick reminder, and I need, and these two are in parallel. When I want with the what you call the current divider, when I want, this is I total. When I want the current through, let's call this R1, this one R2. When I want the current through R2, I use R1. So I R2 is equal to R1 over R1 plus R2, R total, R1 plus R2 times the incoming current times I total. When I want R1, when I want the current here, I use that resistance here. It's rather a ratio of rejection. So the current rejected by that comes here. The current rejected by that goes there. Okay, so this is a rejection ratio. So this is going to be R1 plus R2 times the I total. Why? This is the current rejected by R2 is sent to R1. This is the current rejected by what? This is a rejection ratio. Remember, resistance is rejection. Okay, so we use the resistance of the other part to get the current for this part. That is how our current divider works. So just a reminder there, I think people knew that already. So I just want people to be with me when I'm doing this. So I want the current through that network, the R parallel 4 network. I'm going to use 4. 4 over the total 4 plus that parallel network RP4. Okay. Oh wait, why am I talking about a current that I don't have? I don't have IT. I haven't calculated IT. Well, everything I've said has been good and true, except that I jumped the gun here. I should have first worked out IT, because I'm going to share a current, but I don't know what the current is. So I should work out IT first. IT is simply V supply over RT. And that is, we actually skip the easy part here, 10 divided by 7,049, and that gives us the C. So that's 10 divided by C, recall C. 10 divided by recall C. I put the RCL and I say recall C. You see that it does say 10 divided by C. I hope it's clear, because I'm trying to avoid the reflection, but you can see there 10, there is 10 divided by what? By C. I said recall C to get to that. Okay, so now we come here and it therefore gives us an answer of a total current of 1,419. Okay, and this is 419, 4186, so I rounded off to 419, and this is amps, and this is only 3 decimal places. It's not our answer. Our answer is long, so I have to store this answer here, store this answer in T. STO, T, very easy. If you're using a sharp, no second function, no nothing, you just hit the STO function button, that green button there. In case people don't know what I'm talking about, it is that green button right here. STO, that green button right there. As you can see, it's written STO. That button there. Alright, so you hit that button there and you record your C and you divide, and there is your answer. Now, IT is that. Now we can go and say, what is I R parallel 4? Maybe let me call it that. I through the parallel network, that parallel network, which you call R parallel 4. The current through that parallel network, which is the current through the 3 ohm, this 3 ohm resistor, is going to be I R parallel 4, I don't have to underline, is equal to, I want the current through this branch, so I'll use this branch. Rejection, remember, is what has been rejected by the 4 ohm, 4 over, and over 4 plus, not R total, 4 plus the 2 that are sharing, is a ratio thing. So there is R parallel 4, 4 plus R parallel 4, which is 2,049. R parallel 4, let me just do that first. They are sharing IT. First, let to understand where we get this from. So it's 4 over 4 plus 2 is 6, 049. This is rounded off, so I'm not going to use 6. I'm going to use 4 and they recall this number. Okay, I think that was B or something. Did we? Oh, we messed up, didn't we? No, we didn't. We didn't. We have these values. We do have these values. All right. So this is that times an I total of what? Of 1,419. All right. So that times, recall D, that was in D, times recall C, no. Okay, that was, remember we have to add 4. We have to add 4, so I'll say 4 times recall B. No, not plus, not times, plus is 4 plus recall B. Our RP4 is B, so it's 4 plus recall B. Where is B? Now there is 2,0 something, 2,049, yes. So I have an answer of, what did I do here? I did something wrong. No, I did something wrong. Our answer is D. Recall D. 1,41. Yes, it is times. Oh, I forgot 4 over. 4 divide by the sum of 4 plus recall B. Alright, so now I'm going to have a correct answer. This is going to be 0,938. It's human to make mistakes, but common sense must show you that you've done something wrong. If you get an answer that does not make sense, this is a fraction and is a proper function, so the value you get must be lower than that. You are multiplying something by a proper fraction, it means that this value must be lower than that, because this is smaller, so it must reduce this. So this is 0,938, and this is what? This is current, so it's amps. So now we've got the current. What we are doing here now is we've got the current that is flowing there now. All right. Now that current is going to be shared again by that. I want the current through that IN flows through the 3 ohm, so I have to use the 2 ohm. So I'm going to say, first of all, store this in E. Then I'm going to say my I through, this was through the parallel network, this is the current through the parallel network there, this is R parallel 1, but I can't say my current through the R parallel 1 in this case. Oh, even then I was wrong to say R parallel 4. I was supposed to say current through R series. R series what? This is parallel 3 plus 3 by 2. Yes, this here. Okay. I've made a big mistake here. I've used R parallel 4, and R parallel 4 already includes this. That was a big mistake. No, we've made a terrible mistake here. I'm actually thinking of redoing this because it's going to be confusing people. Okay, there was nothing wrong with what you did until we got to what? To this point here. Where we made a mistake is with IR parallel 4. We are here, IR parallel 4 is the same, the current through the parallel network there is the same as that one here, because the parallel network is that gave us actually the total, not the. So we're supposed to share between this series network and the 4. So this is supposed to be, I don't know whether I should correct this or should just, because I could just go on and say we don't want the current through that, we want the current through the series network. This is going to be, I have to apologize because this is going to confuse some people who are sleeping there, and when you sleep you miss something. This is R series, the last one, R series 2. Okay, R series, I don't know where this comes from. R series 2, this was supposed to be R series 2. Okay, which is 4.2. Okay, we're supposed to say this R series 2, and this is supposed to be R series 2. And this cannot be that, because it's 8.24 and 4.2 is 8.2. But that kind is correct. So we're supposed to say here 4 divided by 8.2. Okay, that times, recall that current here is recall 4.4, no, recall B, recall C, recall D. Yeah, there's my current there. I'm supposed to say recall D times recall D. That's what I don't like. That's why I always mark up with pencils there. Now I don't know where my current was anymore. It's in D, so I'm supposed to say 1,418, and then this here is supposed to give us 0,692. This was 0,692. We slept for a second. 0.692. This is our current here. Okay, because why? I had used the whole parallel network, whereas I wanted that resistance only, the series resistance here, and this one, they are the ones that are sharing. Now I used that resistance there. That was very wrong. I could have used that resistance if I was doing the voltage, yes. If I was calculating the voltage there, I would have used that resistance R power 4. But I'm calculating the current here, so it's this series part, which you call R series 2, sharing with the 4. So it's 4 over the total of this and the series part. That is the mistake that we made them. Now we go on and say, okay, hopefully we didn't throw people off, because we stayed on that for a long time. We didn't realize that mistake for a long time, and you kept talking and talking. Just we chose the wrong value. We didn't really analyze our circuit correctly. Circuit analysis, I think I'm going to discuss circuit analysis, is very important. Now let's come in and say, now we've got the current. That's how I remember, because we've got the current here now. It must come and be shared by these two guys here, because they are in what? They are in parallel. Would have long been done, did not done that mistake. So we want the current through here, so we are going to use the 2. Already said that we want the current through I. It happens to be Norton. Why? Because that is the current that flows through A and B. Once we close that circuit, the current through the 3 ohm is the one that flows through what? Through A and B. This thing keeps doing this. I don't understand why it keeps throwing little dents everywhere. It threw that dent. I think that was done a long time ago. This nonsense here, this here, shouldn't be here. I'm seeing these little disturbances here. Right. We are trying to work out what I said was I Norton. Or did I remove my M's from the last calculation? Okay. I Norton is the current through the 3 ohm. To get that, these two in parallel, we use the 2 ohm already explained with the current divider. 2 over 2 plus 3. We are sharing with the 3. Rejection. What the 2 rejects goes to the 3. So this time the current that comes in, which is I, R series 2, the current that went through this series network, right? So which is equal to 2 over 5 times 0.692. Have you stored our answer there? No, we didn't store our answer in F, the self thing. So our I Norton now, our I Norton is going to be equal to this times 2 divided by 5. And that is 0.276 amps. I'm going to store this in B. I don't need anything else. I've got my resistance in A, my Norton resistance of 4.46 in A. I've got my Norton's current of what? Of 0.276 in B. Remember, this was rounded off. Yes, it was good. This was rounded off. This was rounded off as well. Because it worked from a rounded off. No, it's not worked from a rounded off, but it's much longer than that. So, even if I look at it now, recall B, it's a much longer thing. It's 0.277. Why did I say 76? It's 0.2768. So this is actually 277. I'm sure people were screaming with me there. 277. Because rounding off, the next one was an 8, so I should change the 6 to a 7. Now that we have those two values here, what do we know? We've got a current through here. We've got a current through here, through R Norton. We've got a current through here. We want to know this current. We have this current here, is that one there. So what does it mean? For me now to get this, I've got two values. I've got RL of 1 and then Rn of 4,446. So now I'm gonna share the Norton's current. So to get this current, I need to use, remember, I need this current, so I'm gonna use that resistance. So therefore, our I through the 1 ohm, which is our answer, is going to be Yes, R Norton, the incoming current is I Norton, R Norton over R Norton plus RL times what call this? The Norton current, which makes our life easy. This is going to be R Norton is 446 rounded off 4,446 divide by, these are rounded off figures, so I have to go to the stores, divide by 4,446 plus 1 times the current of 0,277, and this is going to give us, okay, so I'm going to simply say recall A, divide by, open the bracket, recall A plus 1, no, I didn't do it correctly, recall A plus 1, and then this times 0.277, no, recall, delete, I almost made the typical student mistake, recall B, remember this, we can't use random value, I almost used the random value there, I must recall my answer from B, and there as you can see, same answer that we had from what? From Thevenin's method, there 0,2259 whatever, which is 0,226. So as you can see, the two methods gave us the same answer. Why is this happening? Why is this happening? This thing keeps happening. 0, as you will recall, this was our answer from Thevenin's method. So as you can see, the two methods give us the same what? The same answer, therefore, and they have to, because they are both correct. Okay, they've been proven over time. All right. So hopefully, when we made a mistake of the R parallel 4 there, I hope you understand why and how we corrected it, and then hopefully you will not run, of course, away too much to not recover. All right then. This was easy, I think. I don't know what you think, but this was easy. So obviously now, what's the difference? If there is a change, if you change a value and if you want to calculate that same current, if you change that to 2 like we did previously, you no longer have to do this calculation. You just come there and change that to what? 2. Okay. Look out for little tricks. Someone could have asked you to calculate with a load resistor of 1 to calculate the current through the 3 ohm. Simply checking that you do know that the current through the 3 ohm there and the what through the 3 ohm there and the load will be the same. So someone could have said, with your circuit closed, with the load resistor connected, what will be the current through the 3 ohm? So look out for little tricks. You know, people throwing little tricks, they will still be asking for the same current because the 3 and the RL are in the same what? And the same path, so therefore the current is the same. All right then, good luck. I hope you understood. I hope this was helpful. See you when we discuss. I want to discuss also what call this analyzing circuits. You know, sometimes with Norton and Thevenin's, people get to fall behind because or get to misunderstand simply because they fail to analyze circuits properly. All right then, cheerio. Enjoy yourself. See you next time.